In this video, we're going to take a look at some very interesting properties of the determinant. And the first property we have is that the determinant of the transpose of a matrix equals to the determinant of the original matrix. We can see that this is true by looking at matrix M, a 2 by 2 matrix, and the determinant of that would be 3 minus 7 times 5, or 35. So that would be negative 32. Now, if we take the transpose of that matrix, we flip it basically along the main diagonal, and we see that the only thing that's going to change is the order of multiplication. So we're not multiplying 5 by 7, we're multiplying 7 by 5. So it's still 3 minus 35, which arises from the commutative property of multiplication. So the order doesn't really matter. And that gives us the first property of the determinant. Now, moving on, we have the determinant of an upper triangular matrix. And you can see that in this case, the last number of the last column is 6, just so that you don't think it's 0. So everything that's below the main diagonal actually equals to 0, so that's an upper triangular matrix. So what would be the determinant of this matrix? Let's stop and think about it. And you don't really have to think. If you see a matrix like this, you have to know that essentially the determinant is going to be the product of the terms on the main diagonal. So if you were to, write it out, you obviously would choose to expand using the first column. So that would be 5 times a 3 by 3 matrix. And then you would again use the first column where 4, 0, 0 is, and you would be left with a 2 by 2 matrix, and that 2 by 2 matrix would be just 2 times 6 because, well, 0 times 1 is just going to be 0. And that gives you the determinant, which is essentially a product of the main diagonal. So there's that. And moving on, we have the third property, and it's about taking out factors. Now, be very careful. In case of a determinant, it's not the same as it would be with a matrix. Because in case of a matrix, if you're adding a factor to the matrix or taking out a factor from the matrix, you apply that to all terms simultaneously. In case of the determinant, it's different. You can take out a factor from just one row or just one column at a time, right? So we have this matrix A here, and we're trying to find its determinant. So obviously the numbers here, they don't look nice. They're just, they're not convenient to calculate. So what we can do is, by looking at the rows and the columns, we see that there's an opportunity for us to factor out 5 from the first column. So let's take that factor, and we're left with negative 3, 5, and 7. So the factor remains outside of the determinant, but it doesn't go anywhere. You still have to multiply the final answer by that factor. So we have 5, and now it's not that we can also multiply a row or column by that factor. So it's not that we only can take it out. We can also factor it in. So what we're going to do is we'll multiply the third column by that factor we just took out. And it's going to give us negative 1, 10, and 1 over 2. Right? So this already looks better. And the last thing we're going to do is we will take out negative 1 from the first row. So we'll just be left with 3, 1, and 1. So this already looks much better, and I'd say you can go ahead and calculate the determinant using the first row or the last column. Both look equally attractive. So, and the answer to this, I'm not going to calculate it here, but it should be 389. So that's what you should be left with. Now we're moving on, and here we have a monstrous matrix B, and I just want you to calculate its determinant. Go ahead, I'll wait. But no, I'm kidding. You don't have to do that. If you paused the video before I said that, my apologies. Too bad. But the thing is, you can actually save yourself so much time if you just examine this matrix and you find that the second column here is actually proportional to the third column. And what that means is that there is linear dependence here. And essentially what that means for our determinant is that it's going to be 0. So the determinant of this whole matrix is just 0. You don't even have to calculate it. You just have to see if there is proportionality. So it could be columns or it could be rows. So perhaps, you could have the first and the second row be proportional, all the same. The determinant is going to be equal to 0. And that is very convenient, saves you a lot of time sometimes. So pay attention to that. Lastly, we have our matrix C, and let's see what we can do here. And the last property I want to tell you about is that you can add rows or columns together by multiplying them by a non-zero factor. So it could be 1, it could be -1. As long as it's not 0, you can do it. And with our matrix C, for example, what we can do is we can multiply the first row by 1. And we can add the first row to the second row, which would change the second row, but the first row remains the same. So the new matrix, the new determinant would look like this. It would be 1, 3, and then it would be 0, 5. So what does that give us? That just gives us 5 as an answer. And you can do that not with just, of course, 2 by 2 matrices. You can do that with a 3 by 3 matrix, with a 4 by 4 matrix, and that's exactly what I want you to do. So here's a matrix D, and I want you to calculate the determinant for that. And we will cover this in a separate video. We will solve this using this last property. So you may leave your answer in the comments, and we will see if it's correct. So this is your homework. If you enjoyed this video, don't forget to subscribe and stay tuned.